So it's a problem 13, chapter 30, problem 13. And what we have here? We have, for example, up to this line, above this line, there is a uniform magnetic field. But below a certain line, zero magnetic field. So there is a border between field, no field. Okay, let me draw that. Let me estimate the amount of space I might need. You know what, let me draw first a dash line. So that's the border line. So above dots out. So let me draw a few dots. So these are dots representing external magnetic field. B external. Here B is 0. Then magnetic field is given. Let me start writing down what is given. So B external is 0.2 Tesla. Then there is a loop of a rectangular shape, but let me show it, something like this, right? So the loop is being pulled out of the magnetic field into the area of no magnetic field. And we're going to discuss only that moment when the loop is crossing this line, right? Crossing this border line. And of course, in the problem, there is a rectangular loop. So let me draw that loop. So let me draw it like this. Oops. So that's my loop, and the width is given. L. L is 5 centimeters. So it's a 5 times 10 to the power of minus 2 meters. Then resistance of that loop is given. Resistance is 0.1 ohm. Here, typical resistance of a piece of wire. Right. Then, now changes which I made. In your homework problem, this loop will be dragged into the magnetic field. I decided to change the direction, and this loop will be dragged out. V. So V is 50 meters per second. Wow, that's quite a speed for the loop. 50 meters per second. So that's what is given. I think I gave you everything. Yeah, I gave you all my heart, right? And we need to find the same question. We need to find current, information about the current, I induced. Again, direction, value, right? Yeah, that's it, yeah. So again, we have a loop exposed to the magnetic field. There will be magnetic flux. If that flux changes, of course, according to the Faraday's law, there will be EMF induced, and current and induced current will be produced, right? So it means that we just need to grab Faraday's law and start applying it, right? So again, so let me write, so EMF equals minus d phi over dt. So that's the beginning, starting point, right? And again, we will have to divide into two steps. Direction, magnitude, or first magnitude and then direction. I don't know why I cannot justify it. Usually I do first a direction. Direction. Yeah, let's do direction. Direction. So again, we need to analyze what happens to the magnetic flux. So 3 parameters, B, A, theta. Right, so let me write lower. B, A, okay, B external, A and theta. All right, and let me start with B. Magnetic field is uniform. Magnetic field is not changing, right? So I can write that B external equals constant. Then area, not area, angle, theta. Again, let me pick a direction of the area vector to be specific. And again, my minor compulsion, I usually pick or align area vector is in the direction of the external magnetic field. So my area will be that way, represented by the green dot. Right. So it means that angle is 0 degrees and anyway constant. Okay, on purpose now I left area to discuss the last. What can we say about area? And that's the first point which I want to discuss, and that's why I usually solve this problem after the previous two. What? Because now, yeah, it's a subtle moment. What can you say about the area? Up to this point, okay, let me say it in this way. Look, area of the whole loop is constant. And that's what we had all the time up to this point. Okay, in the problems about Faraday's law, right? Every time we had a loop, and that loop was fully exposed to the external magnetic field, right? Over here, you see, the whole loop is exposed to the external magnetic field. In the example which I just erased, also, the whole loop was exposed to the magnetic field. And in those examples, we use the area of the whole loop because the whole loop was exposed. But now we have a different situation. Not the whole loop is exposed to the magnetic field, only this upper part. So only this upper part of the loop is going to contribute to the flux, magnetic flux. This part of the loop is not going to contribute anything. It doesn't pay its taxes, right? So only the upper part pays taxes, right? Contribute to the money the government has, right? So it means that although, yeah, the total area of the loop stays the same, but we're not interested in that area. We're interested only in the area exposed to the external magnetic field. You see the difference between those problems and now, yeah, those problems and now this problem, right? That's the first moment which that's why I wanted to discuss this problem, right? Okay, let me write that. And I hope you got this idea, right? So which way I wrote it? Okay, so I will write area and right over here, exposed to be external. And what happens to that area? And even, you know what, I can slightly highlight it sort of like this, right? So that's the area I'm talking about, exposed to the magnetic field, external magnetic field, because only that area contributes to the flux. Okay, and what happens to that area as we drag this loop down? It's getting smaller and smaller and smaller. So that area is going down, right? So as a result, I can come up with the information about the flux, right? Magnetic flux produced by the external magnetic field. See that, guys? But in your homework problem, since your loop will be dragged into the magnetic field, so what will happen to this area? It will become larger and larger and larger and larger, and eventually the whole loop will be dragged into the external magnetic field, right? So that's the first difference between those problems. You know what? Let me even underline this with a red. Right. Otherwise, it will be pretty much the same problem like previous two. Yeah, flux. So magnetic flux as a result is dying. Okay, let me confirm my conclusions. Hold it. Yeah. Damn it, I forgot I changed the statement. So in my solutions, still solutions are for when the loop is dragged up, but so flux is dying. So the loop, of course, doesn't like it. Of course, it will respond with induced current, but it will try to support this dying flux, right? So in this case, the loop becomes supportive, like Florence Nightingale. So I can write B induced will be in the same direction as B external, and again, within the loop, because we're supporting flux within the loop, right? So, and now you remember, usually I like to draw induced magnetic field, dots or crosses. I realized I usually like to use blue color for B external, and now for whatever reasons I change color, sorry, but it's not a big deal. So now B induced will be in the same direction as B external, right? So it means that I must use dots. But now the question for you, right? Okay, I drew a couple, right? So that's, let's say this is my B induced, but the question is, okay, so let me hold you guys a few extra minutes. Should I draw these blue dots only in this upper part of the loop? Or should I draw those blue dots everywhere within this loop? Think for a second. Again, during the normal semesters, when we are in class, when I bug students about this, and many students, they say, you know what, only in the upper, they want to draw these blue dots only in the upper part of the loop. But, okay, I see somebody responded in the chat, right? Everywhere. Yeah, but with an additional guiding question, look, guys, if when I ask them, guys, look, what produces this B induced? This induced magnetic field, that induced current produces this B induced. And where does this induced current flow? Of course, that induced current flow in the whole loop. Induced current cannot flow just in the upper part of the loop. Current must flow in the whole loop. Loop must be closed. So since induced current flows everywhere, of course, this induced magnetic field will be everywhere, not just in the upper part, right? See the physics, see the difference, right? So now I can draw, that's the second part, which, and I like, that's why I like this question. I mean, this problem. So that's our B induced. So of course it must be draw. It's not that big a deal. It's not going to change the solution, right? But it's good to discuss, right, to have a deep understanding of the situation. Right, so now we have direction of the induced magnetic field. And so now right-hand rule, dots, it means out, dots out, right? So it's this situation. So it means that I have to position my fingers like this, right? Yeah. So my thumb, you see, gives me this direction, which is counterclockwise again. So counterclockwise, yeah, that's correct direction. And let me use red. So that will be. So that's our I induced. I induced, right? So I induced in CCW direction. Every time it reminds me that company on hockey helmets, right? CCM, I think, right? But here, if you flip M, it's CCW, right? Right. Okay, guys. So pretty much we found direction, right? Then it will take probably a couple of minutes to find the magnitude. But at this point, you should be able to do it by yourself. I will send you my notes. I will send you no, I will not send you my notes, right? Let me write it quickly, right? Because my solutions are to the solution of the problem. So let me write quickly. So magnitude. So EMF equals to absolute value of d phi over dt. And of course, the first step, like in the example which I erased, so a magnetic flux equals to B external dotted with A, right? And of course, the angle is 0 degrees. You see, steps are very similar. So immediately I can write it as B external times A, right? And of course, I will plug it here. So it will be d over dt B external times A. I move faster because we've done exactly the same steps, right? Couple of times, right? All right, so now what can we say about B external? It's constant, right? So this is constant. So it means that we can extract it from the sign of differentiation and out of the sign of absolute value. So we can write B external and absolute value of rate of change of dA over dt. It's like an example which I just erased, right? And again, aerial velocity. In order to pass this stage, in order to make a smooth transition, it makes sense to introduce this auxiliary distance. I think I used this x, right? So let me check. Yeah, I use this x. Right, so let me introduce this x auxiliary, just temporary, just for a second. Right, so again, I will introduce that x. So area will be Lx. And as a result, we will get, again, L can be extracted like in the previous example. So it will be B external L and dx over dt. And dx over dt is the velocity. Okay, so that's pretty much the end. So B external times L times V. Right, so that's the value of, if you plug, you will get the value 0.5 volts. And of course, current, it will be EMF divided by the resistance, and of course it will be 5 amps. Okay,